So I'll start with introducing our panelists. So first, George Markomanolis is a lead HPC scientist at CSC IT Center for Science in Finland. His research interests are on performance evaluation optimization of HPC applications and parallel I/O analysis on various file systems among porting applications to new technologies. He is also a member of IO 500 committee. In his current role, he explores programming models for the Lumi Supercomputing, among other activities. He is an expert on using many profiling tools, understanding the bottlenecks, and proposing solutions. Before joining CSC, he was HPC engineer at Oak Ridge National Laboratory, a computational scientist at KAUST, and a senior engineer at Barcelona Supercomputing Center. He obtained his master's in computational science from the Department of Informatics and Telecommunication at National and Kapodistrian University of Athens, Greece, and his PhD in computational science, computer science from the École Normale Supérieure de Lyon in France. Welcome, George.
Thank you.
Our second panelist, Jordi Blasco, is a computational physicist from the University of Barcelona, Spain. Jordi has more than 17 years of experience in high-performance computing in industry and academic environments, more than 12 years of experience as a solution architect on a mission-critical environments, and also more than 12 years of experience in leadership and coordination of cutting-edge HPC projects. Jordi has a solid background in parallel programming, performance analysis, application tuning, and HPC system administration. Jordi is a very active contributor to several open source projects dealing with HPC and large-scale systems, and he has worked as an independent advisor for several companies and research centers. Jordi is also the founder of popular HPC knowledge portal hpckp.org, and co-founder of HPC Now, hpcnow.com, a global consulting company focused on HPC. Welcome, Jordi. So we have a person from Finland, we have a person from New Zealand, and now I'm actually turning into the office right next to me, where my boss Ugo Varetto, CTO of Pawsey, sits and is connecting to the session today. So the tree actually that you can see in the background is the same tree that you can see in Ugo's background. So Ugo Varetto, the Chief Technology Officer of Pawsey Supercomputing Center, is an accomplished technology leader and computational scientist. His focus is on data-intensive HPC, large-scale parallel I/O, accelerators, and quantum technology. He has held key roles in significant research projects such as the EU-funded Human Brain Project, has contributed to numerous projects with the European supercomputing infrastructure, and has worked in commercial companies and government and academic institutions in the US, Europe, and Australia. Ugo has been developing GPU-accelerated scientific software since 2006, and is currently working on designing scalable scientific computational solutions or hybrid CPU-GPU systems and implementing large-scale real-time data processing and visualization workflows, while supporting international research projects such as Square Kilometre Array. He is also involved in quantum technology research projects, including the acquisition and operation of a diamond quantum computer at the Pawsey Supercomputing Center. So welcome to all panelists, also welcome to all the participants of the panel. And I'll jump straight into the first question, or maybe topic, that I have prepared for this session. As this session is focusing on programming techniques, we know what your professional background is already, but we would like to ask you to introduce yourself as programmers as well. So what is your programming expertise? What languages do you use, and which GPU programming techniques you prefer to use in your everyday work or support of various partners that you are working with? And I was thinking that maybe we can ask George to start, and then Jordi and Ugo.
Okay. So as programmer, basically I would say my PhD was about MPI and predicting application performance on MPI. So how to understand all the MPI internals, how it works, and simulate codes. I worked a lot with task-based programming model, like on PSS from Barcelona, and porting parts of weather models to PSS and overlap with tasks, communication and computation. Porting algebraic multi-grid codes to OpenPSS again with tasking, optimizing seismic codes in C, porting codes in C++. I'm tuning a lot of I/O and profiling with various tools. I would say as language, I had more experience with C. I have used Fortran when I have to use C++, which of course for me it's a kind of, it's a bit beast like C++. Python had also like a Python case for the AMD system. So language is about what is a project basically. So you have to adjust and try to learn. I don't have one that work all the years, I would say. Of course, scripting, etc., is different aspects, but language depends on the project. But I'm familiar with the main HPC, if I can say, language is the C++, Fortran. Now, by GPU programming techniques, what do you mean? You mean like the overlapping stuff, etc., or what do you mean with this?
I think in your talk, you were going through many different programming models, like the ones based on directives, the ones, the new ones that are like Raja, or Cocos, or Alpaca, or pure, I mean, or maybe CUDA, or maybe even OpenGL. I think if we get to Ugo's introduction as a programmer, he will probably also mention programming GPUs as OpenGL. But yeah, that was the question about what kind of, if you would have a researcher coming to you and asking, what should I use, right? I have a C or a Fortran code, and what should I use to port my application to GPU? Okay,
whatever I answer, I'm politically incorrect because I represent CSC at OpenAP ARB. So I should say OpenAP, but let's be realistic. I mean, the answer, I mean, what's my favorite? I would say OpenAP because I have more years experience with OpenAP. I would say SQL because I believe SQL has portability. Cocos has a lot to learn more. You can get worse performance easier. And Alpaca has great performance, but it's a bit more unknown, I would say, but has really great performance. I would go with OpenAP, but you know, it depends on the kernel, I would say. And the language, of course, right? OpenAP is in every language. So if someone comes with Fortran, OpenAP will be high in my list. If you come with C++, I would say profile and depend on the kernel. So see the performance before you decide which programming model you want to use. There are so many that there's many ifs to decide which one to use. And I would say go with the one that you know already. And if you are not satisfied with the performance, then change, then investigate and change to another one.
Thank you, George. Jordi, how about you?
Okay, so in the discussion, so my background is in computational physics, but I have been involved in the development of several codes with very different scientific domains. From physics, obviously, but computational chemistry, life science in general, and so on. My experience in parallel programming is mostly in traditional HPC. It's OpenMP and MPI. Most of my experience is oriented to performance analysis and code tuning, and to improve obviously the performance, the efficiency, and the scalability of existing code. Having said that, I also contribute to some CUDA codes, but as mentioned, my experience is mostly focused on traditional HPC. So in terms of preferred languages, as a computational physicist, and I'm not going to be very popular with PhD students and new people in HPC, it's Fortran. Fortran and C++. Those are the ones that I feel very confident with. But I had these discussions already as George already. So if a new researcher comes and asks me, what should I use as a parallel programming language, I will suggest to explore high productivity parallel programming language called Chapel. It's developed by Cray. Now it's a consortium and it's open source and so on. It's led by Cray anyway. And Cray, well, now HP has a lot of FTs, a lot of people involved in the development of that code. And at the end, you need to, this is especially for new PhD students that want to get into this world. And the time that you have to invest in learning MPI, OpenMP, Fortran, or C, and the time that you need to carry on your thesis, it's limited, three years, something like that. So learning those things will take half of your lifetime. And if you want something that can produce the results quickly as possible, don't take the lead to something like R or Python or Java. So there are other tools like this one that maybe, at least for prototyping, will work just nice. And then if you are looking better performance, as George said, so then it's time for you to mature the code, to explore different options, and to go towards a better tool, better coding strategy. Okay, and yeah, that's pretty it.
Cool, thank you so much. Ugo, over to you.
Yes, thank you. So much as you indicated before, so I started working as a graphics programmer in 1994, right? So I was trying to do linear algebra on an SGI reality engine GPU and the geometry engine, which was implemented with the Intel RISC processor, right? So that's how I started my journey, with GPUs. It's 27 years, right? So I did start like that. So I have always used mainly C++ and assembly language, because they had to really squeeze the last bit of performance out of anything we were doing, right? My experience was working as a computer scientist and software engineer in commercial companies until 2006. I then moved to work on HPC related matters. And again, my preferred language is C++, but I think all the other speakers gave I would say the correct answer. At the end of the day, it's about what you're trying to achieve. I don't think it makes sense to just select a language up front, right? There was mention of Chapel. I did use Chapel. I was working at Cray, so I did use Chapel. I even gave presentations on Chapel. These meetings being recorded, right? So okay. So I will say that it is very true what it was just said before. It's in terms of productivity, it's hard to beat Chapel because it has built-in constructs, right, that automatically take care of, for example, data distribution and data exchange. It's very simple to extend your code to go from single node to multiple nodes, right, and multiple threads. So absolutely, that's something that could be considered, but it really depends on what you're looking for, because it depends also if you need to access low-level optimization or not. So as I told you, Maciej, even with C++, if you surround your code with two brackets, the generated assembly changes, right? So it really depends what you're looking for. If you need to really go down to the level of dealing with low-level optimization, you don't have options. You cannot use directives. You can only use, even Fortran is probably okay, but C++ and assembly, right? It really depends what you want to use. One thing I need to mention as well, you talked about which programming languages we have used. I've used pretty much everything you can think of, including Haskell. We did port, this is not a joke, Fortran code that was simulating climate Fortran code to Haskell using GPUs, right, in 2010. The result of that experiment is that the code was one-tenth so of the Fortran code, and it was running 4 times lower, right? That's so it really depends what you're looking for here, right? I think we have a question later about software engineering practices. I'm not going to talk about that, but so to answer the question that others have answered, right? If somebody came to me today asking what they should be using, I would just first try to understand what they're trying to do, and then also suggest to look at all the options, including Chapel, including Rust, including any language that is good for the job, right? That's my answer. So, yeah.
Okay. Thank you all. And this is, so this is for the introductions. I will also say, yes, I'll clarify this. The session is recorded, but if you want to say something that shouldn't be recorded, then please go ahead and we'll make sure that
look, Maciej, it was just a joke.
No, we want to keep it as an open forum. So
no, but look, Maciej, just a joke. The thing is about Chapel, right? Just gonna say this. Cray is required to produce every year a report about the status of that language, right? It's very well documented for a specific reason, despite not having that many people officially using it, right? So there are some specific communities which you never hear about who are using Chapel, right? To do work that we cannot discuss now. So yeah, yes.
Okay, thanks.
Yes. Yes.
For the rest of the panel, I will try to go through a couple of topics that we have provided. So I'll ask panelists to share their opinions, but please feel free to use the chat also if you would, or just unmute yourself and speak. I think with the number of participants we have on the call today, we should be able to accommodate that as well. So please feel free to join the discussion in whatever way you prefer. And one of the first topics that I wanted to propose as a discussion is heterogeneity of supercomputing systems. So as we all know, Pawsey is preparing to provide access to heterogeneous CPU, GPU systems, photonics. But during last SC21, so supercomputing conference, there was a lot of discussion about heterogeneity and whether it is the only way to achieve next amazing levels of performance, such as Exascale. So such discussion is, of course, directly related to programming models and techniques that you are using for and optimization strategies as well. So what is your opinion on that? Is building systems like photonics the only way, or maybe we should be like looking at other strategies and also other programming models, you know, because that's tightly coupled.
Should I start? Yeah, yeah. I mean, I think what is maybe missing is amazing levels of performance. What about the science? I mean, it should be, because in my mind, I mean, Exascale is one part, science another part. I hope they overlap enough and not just pay just to have the best SPL or whatever. As you understand, I'm a bit against the SPL stuff, etc. So the truth is that there are plenty of heterogeneity, and I mean, and outside of Europe and US, I mean, like, okay, Fugaku and China has its own stuff. It seems that for performance, at least, you cannot continue with the classic CPUs. That, okay, even for power consumption and that's even more and more, you need accelerators. Now, what format will be this accelerator in the future? If it will be like a FPGAs or something else, I don't know. For now, at least FPGAs seems quite complicated. I mean, scientists will not go there. If maybe programming models like Cyclic can help on this part. But I think we're quite far to say that something outside from GPU is the default device for performance. I think the CPUs are here a long time. Now AMD and Intel are in the game. I hope that Aurora also will be delivered one day. But I mean, we're still it's still early to be able to see in 10, 15 years what's the proper device for heterogeneity. I mean, there are plans from the vendors for the next year, and NVIDIA is releasing Hopper, I mean, soon. I think the plan is like you have 3 GPUs at least with Intel, hopefully, and you use something like Cyclic, right? Cyclic can run on any of them, for example. So OpenAP also, for sure. But I think SYCL, because it has investment from many sides, and I mean, Intel is pushing for this, Oak Ridge with the contracts also is pushing. SYCL seems quite one of the programming models that will exist for long time probably. It depends, of course, of the funding, etc. But I mean, this moment, okay, I hear also about quantum computing. I mean, it's not for the problems that we do on HPC. This is my feeling. I have never accessed any simulator or something, but I hear from researchers, forget it. This is really in the future, and it's not about what we do today. So I believe that the GPU-oriented hardware, at least, is the one to achieve the performance. Exascale is basically, I would say, here already. I mean, even from China with the processors, etc. But I expect that on June we'll have the frontier at least. So the GPUs is a way for now, I would say. I mean, I don't see something else, because imagine how much code has to be ported to something else. Don't forget that in China, there was hundreds of people working to port weather models, etc. It doesn't happen in one night if you don't have the FTs. So this is really strict thing to happen overnight.
Okay, thank you.
Okay, sorry. Yeah, I'll go next then. So look, I think I'm not sure we're asking the right question here, right? Because do we? So as it was indicated here by others, right? So do scientists even care about what they're running on, right? So do we? What are we trying to do here? Because if you can abstract, right, the programming model well enough, and unfortunately, we have self-driving cars, but compilers to this date are still not able to perform some basic optimizations, right? So I think if they did a better job, right, in developing compilers that can abstract better the hardware you run on, and then we can use directives, of course. OpenMP is a good example, right? Then it's going to be up to the programming model to deal with this, right? If you can specify enough parameters to the directive and stuff, then it can figure out on its own if something should be offloaded or not, or these kind of things. Because right now we don't have choices, right? We only have CPUs and GPUs. For the SK8, there's already been, actually, we already have up in the desert thousands of FPGAs processing that in real time, right? Because in that specific case, the algorithm that we implemented there is very simple and it works very well on FPGAs, right? So you need to use what's required for the job at hand, right? But my point is that we should be focusing more on the programming model and the abstraction, right? SYCL is a good example, actually, very good example. If we had in the future, if somehow SYCL was kind of taking over to some extent, right? And you've started developing code with SYCL, it would make things much easier in the future to port to other architectures, right? And OpenCL today is a preferred programming model for FPGAs, right? So if you had SYCL working properly in the future on a number of accelerators, then you focus more on the problem you're trying to solve and using that specific programming model, and let the software and hardware deal with the rest, right? That's my view on the thing. Yeah.
Okay, thank you. I saw that we also have one hand raised by VASIM, and actually that's one of the things that I wanted to mention, that there is this option, so you can use it to notify us that you have a question or comment. So VASIM, please feel free to speak.
Okay, so yeah, so just a couple of comments. Maybe starting with what Ugo said. Yeah, so I think it would be fantastic to have some more abstracted programming languages to write scientific software code in. I guess the issue with that is that there's a lot of legacy code that exists, and the cost of debugging in terms of person hours is quite significant. And so anytime you think about changing your code to a different language base, there's a significant person hour investment in doing that. And so, you have to factor that into whatever you're going to do, is that, if you have, hundreds of thousands or millions of lines of legacy code that's been debugged and tested and that you know is correct, then if you want to make it run faster, then that's going to cost some time, particularly if you're porting it to a new language. I guess my second comment around technology is that in the current era, I guess we're facing the fact that we have locally very fast compute capabilities. So the GPUs, more or less, I mean, computation is basically free as long as you can feed them fast enough. But there's really these drastic changes in the ability to feed the memory. Firstly, as you go potentially off the GPU to the CPU, although with Infinity Fabric and NVLink, that problem in a sense has sort of been solved to a certain extent. But there still remains the fact that going off node is still extremely costly compared to the speed that you get within a node. And that to me is kind of the main challenge in terms of going forward to sort of address exascale systems, in that you want strong scaling. At some point you're going to run to the limit of what you've got on a single node, and you want to be able to run across multiple nodes and get strong scaling. But yeah, I mean, the speeds that you get between nodes relative to things like Infinity Fabric and NVLink are just different orders of magnitude. And so this is a real challenge. Yeah, I guess the other comment is about, whether or not we'd see, things like APUs become more popular into the future, where the sort of low latency chip and the SIMD chips are sitting much closer to each other and maybe even share a memory space. So I guess those are kind of my comments.
Look, yes. So just one comment about the off-node issue, right? So on the new system, same as Lumi and others, right? Across GPU nodes, we will have an 800 gigabit a second connection, right? So this is not the same as the bandwidth you get on chip, especially on GPUs, right? But it's fully fast enough to be able to scale code off node, right? But there's another consideration to make. So what I'm looking at in these days is coroutines with C++, right? And asynchronous programming. So what might happen in the future is that if you want to scale, right, for some applications, you might have to change the way you write code. So when we ported some of the code to GPUs back in 2010, right, the first thing we did was to, overlapping computation and communication, right? So if you change your code such that you can process while you're moving the data, that will go a long way in addressing some of the problems you addressed, right? You talked about. Unfortunately, you have to literally rewrite everything, right? So this is going to be a problem. I acknowledge that. So yeah, and that's my comment.
Okay. Just a comment around that as well. So I still remember a case study, okay, of a code that I was able to tune and to accelerate quite a bit. Initially, we did the math, and the expectation was that the overall runtime of a particular job to take around 82 years. Finally, we managed to run this on a smaller time scale because it's already completed, obviously. But so that's basically what's happened to a science when you are dealing with a problem that's way too big or that takes too long, and you want to analyze the results on your lifetime. So things will happen, and then you need to look for an alternative, no matter how long it takes and how much effort you need. So there is no other option but to do that. Otherwise, just lowering the expectations. But this is the thing that I usually go against. So I usually encourage the researchers to go to the limit and don't lower the expectations. Go for the thing that you are looking for and to be more ambitious. Okay. Having said that, as you mentioned, there's a cost. There's a cost that's extremely big when you have a legacy code that have been developed for generations, and porting that code to a brand new language, it's so costly. But at the end, if you profile the code and you conduct a performance analysis, maybe you can find this region of the code that doesn't have too much lines of code that consumes most of the CPU time. That's where the energy, the efforts should be focused on. And then exploring the different options that you have available at that particular moment of the evolution of the HPC is what actually allows the HPC, the code itself, to mature and to get the speed that you are looking for.
Yeah, so Jordi, just one comment about what you just said. What you said is exactly how the Meteor Swiss weather code was ported to GPUs. We identified one module, the dynamical core, which were consuming most of the compute time, not a lot of code. We ported that one bit and only that one bit to C++ and CUDA, but the rest of the code stayed in Fortran, right? And by just doing that, we achieved a performance gain of like 300%, right? So that's, I think, the way to go. Do that little by little, right? One module at a time. That might be the right way. Yeah.
Okay, I will move to another topic. I mean, related to what we were just discussing, but as we see more and more codes are being ported to more or written in the more portable programming techniques, like let's say like HIP, which can use different GPU backends, or other GPU languages like Cocos or OpenCL, or OpenMP as a directive-based example, which will be supported by most of the compiling families. We are looking for our codes to be more portable for various generations and also various platforms of accelerators. But what about the performance portability between those? What is your experience in that respect, and how to make sure? We also had a talk today from Sunita in the morning session, looking at exactly this particular thing. What is the level of support of various features and the performance moving from various versions through various versions of compilers, for instance, and platforms as well. So what are your comments on that?
I assume I start again. So I would say there's no performance portability with a generic aspect, but it depends totally on the developer. The developer has to see the device as something abstract, that I know how to map my resources on this device, but be enough abstract for the next device. So what I mean is that I will not say names. A European organization sent us SYCL code. They have used HIP SYCL on NVIDIA devices. They have seen never AMD device. So I compile it, it runs. I changed nothing, it runs. But it was extremely slower than an NVIDIA GPU. I don't remember, not even V100, lower than V100, older one. So he didn't have enough workload. So I started increasing the workload, but from the programming, he didn't separate the memory between GPU and host. So I had to copy on the GPU from the host stuff that I shouldn't, and the memory crashed before I have enough workload to stress the MI100. So why this happened? Because the developer was thinking, this is my GPU, it works good for this, and without expectations, for another GPU, I need more workload, but because I bring that memory from the host that I didn't separate it to not to copy on the GPU, it doesn't work, even work when I use more workload. So we need to have an abstraction layer on this aspect to say that okay, if I change the layer of heap or something else, I just change the commands and it works, and I have in my mind all the layout like maybe Cocos has, for example. But yes, we don't need to think only about the device, the MI100, the MI200, or whatever. We need to think about even the future, to optimize for this device, keeping in mind that in the future we can have maybe less memory but faster memory or something like that. So to be able to adjust on this aspect. I mean, there is portability, for sure there's portability, but performance totally depends case by case. It's not generic portability. I mean, I think this is the experience that I have.
Okay, so then I'll go next. Good, because George has already answered the question. Really, I was never able. I don't have a lot of experience with the directives, but I was never able myself to achieve performance portability. So you want something which runs at optimal speeds on a platform. As soon as you move the code to another platform, in my experience, I was never able to achieve good performance. I always had to tweak stuff, right? So I kind of agree with everything that George said, right? It really depends what you mean by performance portability. What is it that you're porting to what, right? So, right, even compilers, right? Even compilers, you have to specify the architecture you want to compile to, right? So it's going to be very hard to achieve performance portability without manual intervention, right? That's, having said that, as it was mentioned before, I actually had good experience in the past with OpenCL, which is, you know, it's not a previous generation, it's something else, but that's why you have CL in the SQL name, right? So that did work quite well when I tested, even on Knight's Corner and before KNL, right? And just changing the size of the command queues and making a few tweaks, it did work pretty well, going from GPUs to another architecture. But I think you always need to take into account that a manual intervention is going to be required, right? So that's my view on the matter.
Yeah. Quite common, but it's more the same thing actually. So it's not about performance portability. It's about code modernization or code maturity. At the end, and this is the clear example, when Intel released the Intel Knights Corner and Knights Landing, they initiated this code modernization, or yes, it was called like that, right? In order to improve the code, in order to take advantage of a new instruction sets that are available in the new microarchitectures. Same thing happening here. So it's about evolving your code, because you're not going to just tweak few things in your code and magically start to run there, and it will reproduce the same results, and at the same time will produce exactly the same or better performance, right? So at the end of the day, what we want is to improve the code in such a way that can take advantage of all the hardware capability that we have in the new supercomputer facility. So that's the reality. That's how it works, and it's kind of a trade-off, because we as a users of HPC, we push the technology barriers and the technology vendors to go beyond those limits, and at the end we get something back, and it's a bleeding edge technology that now you have to learn how to use it, and this is the ongoing duty. And for the supercomputing facilities, that they are going to take this new set of bleeding edge technology, they put the risk, they assume the risk of this new technology, and they are going to get, they are going to also collect the glory once they see that thanks to this new capability, they are going to mature the codes, and they are going to be able to achieve even better performance.
Yeah, and you know, technology evolves. So I think about matrix cores or tensor cores, right? They didn't exist until a few years ago. Even just the fact that now you have a lot more memory on the node, right? You don't want to just run the same code you were running 5 years ago, right? Unchanged. You have to make changes somehow to take advantage of the new architecture, right? So.
But I have a feeling that, I mean, everything that we do, so this code modernization that we do for whatever architecture we are working on, hardware architecture we're working on, actually allows for the whole profiling that we are going through, and then, you know, finding this hotspot and then separating that as a kernel actually is leading us to using and implementing some proper software development practices on your code, right? I guess this is this is probably something that we'll be seeing more. I mean, as we are preparing codes for various accelerators, we are also making sure that those codes are written in a way that can be then easier ported to something else, or we are just basically removing some of the performance bottlenecks. But yeah, I'm not sure what's your comment on that, but I also see that Sam did raise his hand. So Sam, please feel free to unmute yourself. And
thank you. I'm concerned, or have been concerned, that the various abstractions that we now have to achieve, I guess, performance portability through pragmas like code or language extensions or libraries have the limitation that they're all pretending that the target architecture can be represented well by a common abstraction. And in practice, that's not always true. It depends very much on the problem. One solution to this can be to, in the program, in the task, make an abstraction at yet a higher level, a logical description that can be translated to hardware-specific backends or even hardware abstraction-specific backends. I know a lot of code does do this with DSLs and configuration time or runtime code generation. But the main difficulty seems to be that the infrastructure that we have available to write such abstractions and convert them is out of reach or primitive, and it's a lot of work. I suspect if we want to get performance portability in the future on yet more exotic architectures, we will need to radically improve this sort of DSL or logic representation code infrastructure so we can use these tools effectively.
Yeah, ideally you want to describe your scientific problem and have a tool to turn that description into code, right? Into running software. I think I know where you're coming from with that question, because I also did work at CSCS on domain-specific languages. I think it's a good idea, but then somebody has to support the DSL. And kind of Chapel goes in that direction in the sense that it's kind of a domain-specific language for distributed computation, right? So, but not domain-specific to any science domain. So that's probably what it is. Maciej, so I saw a question from Emily, which I think it's worth looking at. Unfortunately, I don't have an answer, but I think it's a good question. So you saw that question as well, right? Because I let the others answer. So
yeah, so I'll just read it loudly. So Emily did ask what does the panel think of the state of developer productivity, for instance, workflows and tools, as cluster architectures get increasingly complicated? What do you think are the biggest pain points, and what can supercomputing centers do to alleviate them?
So Maciej, that's a question from us. Sorry, go ahead, please.
Quick comment on that. Many supercomputing facilities around the world, they are embracing and adopting workflow managers like Nextflow or SnakeMake, even though using not just regular workflow managers to interact with this, but even container-centric technologies for doing that. And there are a lot of things going on nowadays, things that cannot disclose, but soon big things are going to be released that can extend not just something from your desktop, but also from the supercomputing point of view to the cloud, and having this kind of abstraction that can encapsulate all your workflow in a way that you can describe everything from the beginning to the end. The reality is that nowadays researchers need a way more than the traditional batch queue system and share file system and a lot of compute, right? So you need research needs a complete workflow in order to complete the whole pipeline and finally get the final results. You don't need to be waiting for the results in order to submit a new a new job or to trigger some actions based on the results of those jobs. Automating all this process accelerates the way the researchers are conducting research, and this is the way to go from my point of view.
Yeah, and actually HPE Cray, they are developing their own, well, they're based on open source tools, but they're developing their own workflow management tools for HPC clusters. The only thing is that it's in the question that I think she's asking about developer productivity, right? So it's about developer productivity. So I'm not sure I understand what that means here. So it's not about research, it's about developers. So I know if maybe Emily, you can tell us more
Maybe
about. Yeah. Okay.
So maybe a good interface for coding or
right. So I don't.
Notebooks.
Yeah, I think so. Emily, if you have issues with the mic. Oh yeah, so
okay. So it's actually both. Okay,
often, yeah, okay.
So it's both. It's really both. Okay. So
yeah.
Workflows and okay. Yeah. Yes.
So Emily commented that yes, she means researchers often are developers, and it's pretty rare to have a research group with a dedicated software person.
Then it's like that. It's good. That's what we said. Probably it's related to this, and also notebooks. I think George mentioned notebooks, like the way you interface with these tools, right? Maybe notebooks could be another good option to simplify the interaction.
Yeah, but usually these tools, I mean, don't really interact with the hardware, right? I mean, they don't depend on if you have a GPU or CPU. That's why it's a bit confusing.
Using also cloud for some specific parts of your workflows. And also making sure that the software is prepared. So we are trying to, as you know, we are trying to address those kind of issues, working closely with research groups through Pacer and other projects.
Yeah. So Maciej, maybe because she's also asking about what do you think are the biggest pain points, right? So as a developer, I always found it very hard to debug large scale applications, right? Just when you put a breakpoint inside your code and you're running on 100 MPI tasks, right? Just because your bug only shows up at scale, that's always been hard to deal with, right? Cray did have and still does have some tools to deal with that specific task of debugging a scale, and also profiling as well. But profiling and debugging a scale, I think that's really the biggest pain point I see as a developer, right? Not as a scientist, of course. So yeah.
So according to the last comment, explains better. I mean, the good thing with the Cray environment is that you can load the module about the MI100, the MI200, and you can remove a lot of flags that you have to do it manually to compile with Clang, etc., to make it easier for the developer to compile. However, for optimized version, no, this depends on the code. I mean, there's nothing. I mean, there's some research for tuning, auto-tuning kernels. I think there's called tool auto-tuning, something like that. But it's not so easy to say that by magic, let's say, let's auto-tune my kernels, etc. I mean, as we do this joke between us, complexity is stability for our jobs. I mean, they were required so to figure out things. But Cray environment, I really like it when it works, of course.
For AMD-based platforms. So from your experience and knowledge, what level of support for OpenACC and OpenMP we might expect on platforms like Cetonix, Lumi, and Frontier and others in future? What those groups should be looking at as a tool to transition from their current setup of the OpenACC-based directive-based approach?